Hi, this is Matt Pelland here to talk about the second half of my compiler. So for the checkpoint, I managed to reach task 88, and now I have completed task 137, so I'm going to be covering in between those two. Though actually, from task 88 until the beginning of R3, there's really not a whole lot going on. With R2, it was really just like supporting your runtime to print out booleans, which is pretty simple, so I'm actually going to just kind of gloss over that and jump in right with R3. So R3 is when we introduced vectors. So in terms of the language, it's pretty simple. You have vector types, which is just an array of other types. And then you have a vector, which is itself just going to be an array of other expressions. Nothing too complicated. Same with the interpreter. Really, not too much had to change here for R3. This is the type checker. You type check every element within the vector, construct a vector type, return that. Interpreting a vector, you interpret all its elements, construct the array, create a vector. Vector ref, you pull out the respective element. Vector set, you set the respective element. And then you just have dummy stuff for collect and allocate. Writing pass functions. One of the interesting ones that we had to do for R3 is expose allocations, in which we separate a vector out into the initialization of its member variables, and then you determine if you need to call collect, and then you allocate the space for the vector, and then you assign all the variables. I actually ended up implementing this as part of the RCO pass, because expose allocations is nearly perfectly RCO valid, except for one line where it adds however many bytes are needed to the free pointer. So you just pulled that out, store it in a variable, and then compare that variable to the amount of space there is, which makes expose allocations perfectly RCO valid, in which case I just put it in RCO, where when RCO encounters a vector, it calls expose allocations on that vector to construct the RCO valid expose allocations output. And then the other interesting thing is the coloring, because vectors need to end up on the root stack. So the way that I did that is down here. So when I go to color a vector, so for my instances, vectors are the only things that I actually typed, because they're the only things that really need type other than in X. So I just make sure that it has a type, which means it's a vector. And then we assign the color with this -1 here. What that indicates is it indicates to my assign color function that instead of finding the smallest positive value that's not restricted, it finds the largest negative value. So basically all of my vectors are colored in a separate space than all of my normal variables, where vectors are colored with negative colors. And so what that does is then when I go to assign variables to registers or stack offsets, if the color is negative, we go down here, and the vector variable is instead a dereference from the root stack register rather than the stack register. So that's how I made sure that my registers ended up on the root stack, which then allows my collector to clean them up, which is where we get to the real interesting stuff, which is in runtime. So we have up here just my initialization of all the different variables you need for the from space, the to space, the root stack, and then I made qhead and qtail just globals to make it easily accessible. And then initialize, allocate space for the from space and the to space, because I wanted to just allocate those once at the beginning and then never have to mess with them again. Allocate space for the root stack, and initializes all the other variables. And then I memset them all to 0 just for ease of debugging. And then down here, once we actually call collect, it is passed the root stack pointer and the number of bytes that it wants to make available, the number of bytes that were requested. So the first thing we do is we set this root start variable to be equal to the root stack pointer, because then we can edit root start without editing the actual root stack pointer, which we want to remain as is. And so it's a double pointer in 64T, so it's basically just an array of vectors. And then both qhead and qtail, which are used when scanning, are initialized to the beginning of the to space, because that's where we're going to start putting all of these vectors. And then, so because the root stack grows downwards, we're going to increment root start until it reaches the end of the root stack. So that's why we have that condition there. And then we first make sure that what we're looking at is actually a valid vector, otherwise it would have been initialized to 0. So that's what that does, and then if it is, we enqueue it, which copies it over to the 2 space, and then we increment root start to grab the next vector in the root stack. And then what that does is that also increments qtail to be pointing to just after the last vector that has been copied to the 2 space, but qhead is still pointing to the beginning of the 2 space. So we're going to call scan on everything in the 2 space, which increments qhead and potentially qtail. But then once those two meet, that means that we have successfully copied over all live vectors into the 2 space. At which point we swap the roles of the from space and the 2 space. We update the free pointer to be that qtail, which is the pointer to the next available space in what is now the from space, used to be the 2 space. And then we just do a quick check to make sure that we actually freed up enough space, because if we didn't, then we literally don't have enough memory to run this program, and we just exit. So what enqueue does is it takes in a pointer to a vector. So this is like an index within the root stack, or potentially an index within another vector. So first we kind of assume that it's going to be copied into that next available space in the 2 space, which is what qtail points to. So we're initializing newlock to be equal to that qtail. And then we grab the actual pointer to the vector itself by dereferencing that double pointer. So object is actually a pointer to the vector. And then a vector's first element is its type, so we pull it out. And then what this is doing is it's checking if that type is within the 2 space, which means that it's a forwarding pointer. So if it's greater than 2 space beginning, less than 2 space end, it's within the 2 space, it's a forwarding pointer. So the new location is actually just that forwarding pointer. That's where it is stored now. And then we set size to 0 just for down here. And then otherwise we actually just copy it over by iterating through all of its elements. Very well, first we grab the size to figure out how many elements it has, which is the second element of a type, because the first element of a type is 3, indicating that it's a vector. Second is how many elements are in it. And then we just copy over every element within the vector. And then at that point we have added a vector of some size to the 2 space, so we want to increment qtail, so it's pointing to after that vector. And then because root was a pointer to the pointer to that vector, we want to edit it so that the pointer to the vector has that new value, which is newlock. And then we also set objects of 0 equal to that newlock, which installs the forwarding pointer, so that other future calls to enqueue will recognize that. And then when you scan, we're looking at what's currently at the head of the queue. And then we grab, once again, we grab its type, which in this case I called it the tag. And then tag sum1, again, is the size of the vector. And so we iterate through and we get the actual element within the object. We grab its type, and if it's an integer, boolean, or unit, we don't do anything. Otherwise, it is a vector, which means that that vector is live, so we want to enqueue it. And then that's going to increment qtail, etc. We're going to call scan eventually on it again. And then we increment qhead by that size, so that when the scan is called again, it's called on the next vector in the queue. And then, if we want to actually see that running, we can go here. So this is just calling my use lots of mem function, so it's going to generate 32 vectors, each taking up 64 bytes. And you can see that that works, but 32 times 64 is in fact significantly larger than the space that I gave it, which is only 256. So without the collector, this would run out of memory. So you can see there that the collector is working, and just as more proof is, you see, if I just make the collector return immediately, functionally the same as just never calling a collector. If I run it then, now that's it, printing out the whole program. But you can see output was none, we failed the test. And then if we scroll up back to here, I jumped back down. You can see right there that the reason for the failure was in fact a seg fault, because we vastly exceeded the available space that I've mallocked, which is only 256. So you can see there just pretty definitive proof that the collector does in fact work, and it does collect. And then, just as a general show, we can run just 100 randomly generated programs to verify that. This is running all of my passes on 100 randomly generated programs. And you can actually see here I'm not running with the optimizer, and I prefer to do my tests without running the optimizer, because the optimizer, if you run it, will result in like some scenarios being impossible because they're optimized out. So running without the optimizer ensures that all of my passes will see pretty much every possible randomly generated sequence of a program, which allows me to make super sure that they're robust. But then I do have this down here, which is an optimization test. I have also tested optimization manually, just making sure that it's doing things that make sense. But then remember this from last time is I passed my random generation an extra boolean, which indicates whether or not to allow reads, in which case, theoretically, if there are no reads in the program, it's fully deterministic, and it should be fully optimized down to a single value, which is what that check does. You can see right there, 100 tests successfully passed, running all of my passes. And then if I just run this real quick, it does in fact fully optimize. So, but then I did also test with reads as well. So now, that's pretty much all I've got for R3. Now we're going to move on to what I've done for R4. So for R4, we introduce functions. So we have things like function types now, which very simple. It's just it has the argument types and it has a return type. And then for an actual function, let's say function definition has a list of parameters, which are typed variables, has a return type, and then has the actual body of the function. Then you have application, which calls a function with any given arguments. Super simple. And then interpreter is also pretty simple. And when you have an application, you take all of those arguments and you push them as if they were that function's parameters into the environment, and then you just interpret the function with those variables in the environment. So like if a function expects an x and y, and then you pass it 1 and 2, you first add to the environment that x equals 1, y equals 2, and then you just run the body of the function, which is very simple. And then for type checking, you just add in I added a separate helper function for function type check, which just runs through all of the functions. First, I add all of the functions to the environment, assuming that their types are correct, and then I check all of the functions, ensure that their body is using the typed variables properly as the right type, and that it returns the right type. And that's very simple. And then, as I've only gotten up to task 137, the only passes that I've actually completed for R4 are revealing functions and limiting functions. And I actually worked this all into my uniquify pass, because uniquify is all about replacing variables with other variables, which is actually really all that reveal fun and limit fun do as well. So it made a lot of sense to just work it into uniquify, because they're doing the same thing. It's just a lot more efficient to have that in one pass. So as for reveal fun, that's just these two lines, because for every function variable, we're going to replace that with a fun ref object, just to designate as a function separate from a variable. So just pushing that into the environment, the way that my uniquify works is it constructs an environment mapping old variable names to new variable names. So this will every time that we see that function, it'll just replace it with a fun ref. So that just working that into uniquify, that's all that had to be done. And then the other step is limit fun. So we first check if it has more than 6 parameters, in which case its new parameters are going to be those first 5 parameters, followed by one vector of all of the other parameters. And so for most of the parameters, they're just going to remain the same for the first 5. But then all the other parameters are going to instead be mapped to a vector ref of that vector argument to extract them. So then when we call uniquify on the actual body of the function, it'll will replace all of the variables within that function with their proper vector refs. And then the other thing that we need to change for limit fun is down here, where we first uniqueify all of the arguments, because that needs to happen. And then, if we're calling a function with more than 6 arguments, we just, instead of passing all of those arguments, we pass the first 5 arguments plus a vector of the other arguments. So that's really all that I've had to change so far for R4, because those are the only passes that I've had to implement so far. So let's see it at work. So this is just a sample program I had for testing limit fun, in which it has a symbol function that expects 8 arguments, and then it just returns a vector of those 8 arguments, and then the actual body of the program just calls that function with 8 arguments. So I'm just gonna, I don't have that outputting right now, but I do have it set up with the debugger. It got moved when I did the checkout. Right here. So unique is now the uniqueified body of the program. So we can see here that it's an application. You can see it's calling F0, and now it is passing those first 5 arguments, and then it's passing a vector of the last 3 arguments, which is correct, because the function itself, excuse me, is over here. And you can see that the function returns a vector of those first 5 arguments, and then for the last 3 arguments, they're vector refs, as expected, and then the parameters are now only 6, because there are the first 5 and then the vector. So you can see there that my limit fun is in fact working properly and replacing functions with what they need to be replaced as. So that's pretty much all that I've had to do for R4, and there we go. Thank you.